Welcome back to the Deep Dive. Today, we are doing something a little bit different. Usually, we're looking at the here and the now, technology, history, human behavior, the things that impact our daily grind.
Mm,
But today, we're zooming out. And I don't mean just to orbit, I mean we are leaving the neighborhood entirely.
we are indeed. We're leaving the atmosphere, leaving the solar system, and heading out into the deep
We're
vacuum.
going to answer a question that I think every single human being has asked at some point. It's usually when you're a kid, right? Lying on the grass in the backyard, looking up at the night sky.
Yeah.
You see those pinpricks of light, those thousands of glowing dots, and you just wonder, where do they come from?
It is the fundamental question of astrophysics, really. How do you build a star?
Exactly.
Yeah.
And we aren't just going to gloss over it with some poetic let there be light kind of answer. We're going to treat this like a literal construction project. We have a stack of incredible sources today. We're talking Carl Sagan, Stephen Hawking, Neil deGrasse Tyson, Brian Greene, the absolute titans of the field.
The heavy hitters, for sure. And what's wonderful about these particular sources is that they don't just give us the math, they give us the narrative. They help us, visualize a process that takes millions of years and happens on a scale that is almost impossible for the human brain to comprehend.
So consider this your step-by-step instruction manual for building a star. If you had the power of a god and wanted to illuminate a solar system, this is exactly how you would do it. But before we get to the construction site, we have to start with a quote that I absolutely love. It's from Carl Sagan, and it really sets the tone for this whole discussion.
I think I know the one you're thinking of. It's iconic.
It is. He says, if you wish to make an apple pie from scratch, you must first invent the universe.
It is such a profound statement. It sounds like a joke at first, a bit of scientific wit, but is scientifically absolutely accurate.
Right, because when I go to the kitchen to make a pie, I'm cheating. I buy the apples at the store. I buy the flour. I buy the sugar. But Sagan is saying, wait a minute, take a step back. Where did the carbon in the apples come from? Where did the atoms in the flour come from? You can't just start with the ingredients on the shelf. You have to ask where the shelf came from.
And that is the mission of this deep dive. To understand the ingredients of a star, we have to look at what the universe provided us with right at the beginning. We have to look at the pantry, so to speak, as it existed moments after the Big Bang.
So let's map out our journey today. We are going to move through 6 distinct steps. It's a recipe, essentially. Step 1, the ingredients, what are we actually made of?
Right, the shopping list.
Step 2, the kitchen, where does this cooking happen? Step 3, the mixing, which involves a lot of gravity.
A lot of gravity.
Step 4, the dough rises, that's the protostar phase. Step 5, the oven turns on nuclear fusion. And finally, step 6, the bell rings and a star is born.
It's a linear journey, but it's one fraught with violence and heat and incredibly delicate balances of forces. It is not a gentle process.
Okay, let's unpack this. Section 1, the ingredients. If I want to build a star, what do I need to go shopping for?
Well, if you're shopping in the early universe, your choices are very, very limited. If you look at the work of Neil deGrasse Tyson and Carl Sagan, they paint a picture of the primordial soup.
The primordial soup. Sounds delicious, but I assume we aren't talking about broth and vegetables here.
Not quite, no. We are talking about the state of the universe shortly after the Big Bang. It was hot, it was dense, and it was very, very simple. After the Big Bang, once things cooled down just enough for matter to form, the universe was essentially a sea of just 2 elements.
Just 2. That's it.
Overwhelmingly just 2. Hydrogen and helium.
That's wild. I mean, I look around my room right now, I see wood, metal, plastic. I'm breathing oxygen. There's carbon, silicon chips in the computer.
None of that existed yet. Or I should say it existed only as potential. Tyson talks about this cosmic fingerprint. If you look at the universe today, the ratio is still pretty consistent with what it was back then. It's roughly 90% hydrogen and 10% helium.
90% hydrogen. So almost everything in the entire universe is hydrogen.
Yes. And it makes sense because hydrogen is the simplest element. It is the fundamental building block. It's just 1 proton in the nucleus and 1 electron buzzing around it. It is the blank canvas of the universe.
And helium?
Helium is the second simplest. 2 protons, 2 neutrons. And as Tyson notes, there were trace amounts of other things, a little lithium, maybe. But for all intents and purposes, if you are building a star, you are building it out of hydrogen gas.
So why just those 2? Why didn't the Big Bang make gold or lead or oxygen? Why did it stop there?
That's a fascinating question of, well, thermodynamics. It comes down to time and temperature. The early universe expanded and cooled so incredibly fast, I mean, we're talking within the first 3 minutes, that it didn't stay hot enough, long enough to cook heavier elements.
Ah,
It
yeah.
managed to fuse some hydrogen into helium, and then snap, the oven turned off. The universe got too big and too cold to make anything more complex.
So we're just left with this universe filled with gas.
A lot of gas, a truly staggering amount. And Tyson makes a great point about the abundance of these elements. He mentions that hydrogen lays claim to more than 2/3 of all the atoms in the human body.
Really, more than 2/3. I would have thought oxygen or carbon.
Well, think about water. H2O, 2 hydrogens for every 1 oxygen. And since our bodies are mostly water,
We're mostly hydrogen.
we're mostly hydrogen.
And we were walking around with Big Bang leftovers in us.
Precisely. The hydrogen in your body is 13.8 billion years old. It hasn't changed since the dawn of time.
That's incredible. So to build our star, we don't need a complex shopping list.
Yeah.
We just need a massive, massive amount of hydrogen gas.
Correct. But here is the problem. You can't just have hydrogen floating around in a vacuum and expect it to ignite. You need a container. You need a place for it to gather.
Right, you need a bowl to mix it in. Which brings us to step 2, the kitchen, or, as the astronomers call it, the nebula.
The nebula, the word itself comes from the Latin for cloud or mist, and that's exactly what they are. These are vast interstellar clouds of gas and dust.
Sagan gives this beautiful visual in the source material. He talks about the constellation Orion, the hunter.
Right, the hunter. Yeah, it's one of the most recognizable constellations, especially in the winter sky.
Most people know Orion's belt, those 3 bright stars in a row. But if you look just below the belt, there's what's called the sword, and the middle star in that sword. And it isn't actually a star at all.
No, not at all. It looks like a fuzzy star to the naked eye, but if you look at it through a telescope, or if you look at the data Sagan discusses, you see it for what it is, the Orion Nebula. It's a stellar nursery.
A nursery. I love that term. It sounds so gentle, so calm.
It is a place where stars are being born, yeah.
Yeah.
But we need to be clear about what the environment is like in this nursery. It is not warm and cozy like a blanket.
No.
It is rarefied, and it is cold. Very, very cold.
Rarefied. That's a specific word. What does that mean exactly?
It means thin, extremely thin. The gas is spread out over light years. In fact, Tyson shares a fascinating story about this in his writings, the story of nebulium.
Oh, I caught this in the notes. This is a great detective story. So back in the day, early astrophysicists were looking at these nebulae through spectroscopes, right?
Correct. Spectroscopy is the tool we use to figure out what the universe is made of. Every element gives off a specific light signature, like a barcode. You know, if you burn salt, you see that bright yellow. If you burn hydrogen, you see specific red and blue lines.
And when they looked at the nebula,
They saw a barcode they didn't recognize, a bright green line. It didn't match hydrogen or helium or carbon or anything on the periodic table. They were stumped.
so they did what scientists do. They hypothesized a new element. They called it nebulium.
Which makes sense, right? We found it in a nebula. Let's call it nebulium. It sat there as a mystery for quite a while. They thought maybe it was some exotic new element that only existed in these deep space conditions.
But it turns out there's no such thing as nebulium.
Spoiler alert, no, it was actually just ordinary oxygen.
Oxygen. But wouldn't they have recognized oxygen? We breathe it every day. It's right here in the room. How could they miss it?
That's the key. On Earth, oxygen atoms are crowded together. They are constantly bumping into each other billions of times a second. But in a nebula, the gas is so thin, so rarefied, that an atom can go for, minutes, hours, even days without colliding with another one.
So they're like socially distanced atoms.
Precisely. And because they weren't colliding, the electrons in the oxygen atoms were able to do things that could make these energetic transitions that they never get the chance to do on Earth because they'd get interrupted by a collision. Nebulium was just the signature of oxygen breathing freely in a way it never could in our dense atmosphere.
Wow. That really drives home how empty these clouds are. It's not like a thick fog bank in London. It's thinner than the best vacuum we can create in a lab on Earth.
And yet, because they are light years across, they contain enough mass to build thousands, even millions of suns. It's a paradox of scale. Low density, but an absolutely massive volume.
So we have our hydrogen. We have our dust, which Sagan mentions includes heavier elements from previous stars, the spice in our soup, and it's all just hanging out in this cold giant cloud.
Yep, just floating there.
But a cloud isn't a star. A cloud is just a cloud. How do we get from a cold, drifting mist to a burning ball of fire?
That takes us to section 3. We need a trigger. We need something to start the collapse. We need to mix the ingredients.
And the spoon that stirs this cosmic pot?
Is gravity.
Gravity. But wait, you just said the gas is super thin. Does it even have enough gravity to do anything?
Everything with mass has gravity, even a single atom. But you're right, the gravity of a diffuse gas cloud is incredibly weak. However, as both Hawking and Sagan point out, gravity is opportunistic.
Opportunistic. I like that. It sounds like it's lurking, waiting.
It is. The universe isn't perfectly uniform. It's not perfectly smooth. There are lumps.
Lumps? You mean like lumps in oatmeal?
Sort of, yeah. Just tiny irregularities. Regions in the nebula that are just a fraction of a percent denser than the regions next to them. Maybe a supernova shock wave from a nearby dead star pushed some gas together. Or maybe it's just a random quantum fluctuation. But once you have a lump, however small, gravity goes to work.
Because that lump has slightly more mass than the space around it.
Exactly. So it exerts a slightly stronger gravitational pull. It pulls in the gas molecules that are right next to it. Now, the lump is a little bit bigger.
Which means it has even more gravity.
Which means it pulls in gas from even further away. It's a runaway process. It's a positive feedback loop.
It's the snowball effect.
Perfect analogy. A snowball rolling down a hill. It starts small, but as it rolls, it gathers more snow, which makes it heavier, which makes it roll faster, which helps it gather even more snow.
But in this case, the hill is the center of the lump. Everything is falling inward toward that center of mass.
Correct. This is sometimes called the Jeans instability, after the physicist James Jeans. Once a part of a cloud gets heavy enough and cold enough, its internal pressure can no longer hold it up against its own gravity, and it begins to implode.
And we are talking about a collapse on a truly massive scale. We're taking a cloud that might be 100 light years across and shrinking it down.
Yes. Down to the size of a single solar system. That is a collapse factor of millions. It's an unimaginable compression.
So the atoms are getting really, really crowded.
Very crowded. And this brings us to the interaction of forces. As this gas falls inward, two really important things start to happen. One affects the shape of the cloud, and one affects its temperature.
Let's talk about the shape first. This brings us to section 4, the formation of the protostar, and specifically the spin.
Yes, the conservation of angular momentum. This is a fundamental law of physics you just cannot break.
Okay, let's unpack this. Hawking uses a classic analogy here, one that anyone who's ever watched the Winter Olympics will recognize immediately.
The figure skater.
The figure skater.
Right.
So you picture a figure skater on the ice. She pushes off and goes into a spin. Her arms are stretched out wide, and she's spinning kind of slowly. Then what does she do to speed up?
She pulls her arms in, tucks them in tight to her chest.
And what happens?
She speeds up. Dramatically. It's instantaneous.
Why? What's the physics behind that?
Physics demands that angular momentum be conserved. If you make the spinning object smaller by pulling your arms in, you reduce the radius of the spin. The speed of rotation has to increase to compensate. The total spin energy, for lack of a better term, has to stay the same.
And a nebula is doing the exact same thing.
Exactly. The initial nebula is the skater with her arms stretched way out light years wide. As gravity pulls those arms of gas in, shrinking the cloud down, that tiny slight initial rotation it might have had gets amplified. It spins faster and faster and faster.
And this prevents it from just collapsing into a single dot, a single point, right?
It does. It creates a disk. The centrifugal force, the outward flinging force from the spin, is strongest at the equator, so it flattens the cloud out. That's why our solar system is flat, like a dinner plate. That's why all the planets orbit in more or less the same plane. It's a fossil record of that original spin.
So we have a spinning disk of gas, but we also mentioned heat. You said the cloud was cold before near absolute zero. How does it get hot?
It was. But think about what happens when you cram things together. The atoms are rushing inward, driven by gravity. They're picking up an incredible amount of speed, and then crash.
They collide.
They slam into each other. And just like clapping your hands together makes them sting and feel warm, these atomic collisions convert that energy of motion into heat. It's essentially friction on a cosmic scale.
So the center of this cosmic snowball is getting hot.
Incredibly hot. Millions of degrees. And it begins to glow, not from fire, but just from pure heat. At this point, we call it a protostar.
Protostar. So is it a star?
Not yet. And this is a really crucial distinction that the physicist in me wants to clarify.
Please do. What's the difference?
A protostar is glowing, yes. It is extremely hot, yes. But it is not generating its own energy yet. It is just radiating away the heat that was generated by the collapse.
Okay, so it's like, imagine an electric oven. You turn it on, and the heating element starts to glow red. It's hot, it's giving off light, but it's not burning anything. It's just releasing energy that was put into it by the electricity.
That is a perfect analogy. The protostar is glowing from the energy of gravity, the falling of the gas. But to be a true star, a main sequence star, it needs a nuclear heart. It needs to turn on its own fusion reactor.
So a protostar is basically a very hot, glowing ball of gas that is still shrinking and heating up.
Exactly. And if it doesn't get massive enough, it never makes that final leap. It stays in this state, cools off over billions of years, and becomes what we call a brown dwarf. Or, if it's even smaller, a gas giant planet like Jupiter.
Right, Jupiter. I've heard Jupiter described as a failed star.
It is, in a way. Jupiter is a big ball of hydrogen and helium. It's hot in the middle. But it wasn't massive enough. Gravity couldn't crush the center tight enough or make it hot enough to start fusion. It failed the audition to become a star.
So how do you pass the audition? That brings us to Section 5, the ignition, the moment of truth.
This is the critical step. You have to force hydrogen atoms to merge. You have to get them to fuse. And nature really, really doesn't want to do that.
Why not? I thought gravity was pulling them together. It seems like they should want to stick.
Gravity pulls them close, yes. But when you get down to the atomic level, you run into a different and much stronger force. Brian Greene discusses this beautifully in The Elegant Universe. We have to look at the nucleus of the hydrogen atom.
Okay, hydrogen atom, that's one proton.
Right. And what is the electrical charge of a proton?
It's a positive.
And what happens when you try to push two positive ends of a magnet together?
They repel. They push each other away as hard as they can.
Exactly. This is electrical repulsion, or sometimes called the Coulomb barrier. As these protons rush toward each other in the super dense center of the protostar, they see each other's positive charge, and they slam on the brakes. They deflect. They refuse to touch.
So how in the world do you overcome that?
You need speed, you need violence, you need heat.
How much heat are we talking about?
Sagan and Hawking cite the number. Approximately 10 to 15 million degrees Kelvin. That's about 27 million degrees Fahrenheit.
10 million degrees. That's just unimaginable.
At that temperature, the protons are moving so fast, they are vibrating so violently in the core that they don't have time to be repelled. They can smash into each other before the electrical force has a chance to push them apart.
But wait, I remember reading in Green's section that even at 10 million degrees, classical physics says it's still not quite hot enough. The protons should still bounce off.
You caught that. That's a fantastic point.
Yeah.
This is where the universe gets weird. This is where quantum mechanics comes in to save the day. It's a phenomenon called quantum tunneling.
Tunneling, like digging a hole through a wall.
It's a pretty good analogy. In the quantum world, particles aren't just hard little balls. They also behave like waves. They're fuzzy. Their position isn't perfectly defined. And because of this fuzziness, what we call the Heisenberg uncertainty principle, there is a tiny but non-zero chance that a proton can simply appear on the other side of that repulsive barrier.
So it doesn't climb over the wall, it just sort of teleports through it.
The proton essentially cheats. It tunnels through a barrier it shouldn't have enough energy to overcome. Without this quantum cheating, the sun would not shine. The stars would not ignite.
Wow. Okay, so it cheats its way through the barrier. What happens then?
Once they get that close, another force, a much more powerful but much shorter range force, takes over. The strong nuclear force.
A strong force.
Sagan calls it the hooks. Imagine the protons have these tiny, super strong Velcro hooks on them. The hooks are very short. You have to get the protons practically touching for the hooks to latch on, but once they latch, they are bound together. And that process, that binding, is nuclear fusion.
So walk us through the reaction. What are we making here?
The basic process in a star like our sun is called the proton-proton chain. We are taking 4 hydrogen nuclei, so 4 individual protons, and through a series of steps, we are mashing them together to create one helium nucleus.
We're doing alchemy, we are transmuting the elements, we're turning the ingredients into the pie.
We are, but here's the most important part. The part that powers the universe and makes life possible. If you were to put the 4 protons on a scale at the start, and then weigh the 1 helium nucleus at the end, the helium weighs slightly less.
Wait, matter was lost. How is that possible?
A tiny fraction of the mass disappears. About 0.7% of the original mass is gone.
Where does it go? You can't just lose matter. Conservation of mass, right?
It becomes energy. This is Einstein's famous equation. E equals mc squared. Energy equals mass times the speed of light squared.
I see. So m in that equation is that tiny bit of missing mass, and c is the speed of light, which is a huge number.
An astronomically huge number. And you square it, so even a tiny, tiny bit of mass, when you multiply it by that massive number, creates a staggering amount of energy, E.
And that energy is released as what? Light? Heat?
It's released as a photon, a high-energy gamma-ray photon, a blast of pure energy.
And this leads us to our final step, section 6. A star is born. Because once that fusion starts, everything changes.
It is the turn-on moment. Suddenly, the core isn't just hot because it's being crushed. It's now an engine. It is a self-sustaining thermonuclear bomb going off continuously in the heart of the star.
Sagan has this incredible description of the photon's journey. So a photon is created in the core. Does it just shoot out into space instantly? I mean, it's light.
No, and this is something that blows my mind every single time I think about it. The core of the sun is so incredibly dense, remember we crushed a nebula down to a ball, that the newly created photon can't travel more than a fraction of a millimeter before it slams into another atom.
So it's like trying to run through a completely packed concert crowd. You can't get anywhere.
It's worse than that. It gets absorbed by an atom, then it gets re-emitted in a random direction. Then it hits another atom, gets absorbed and re-emitted again. It bounces around in what physicists call a random walk. It can take, on average, 1 million years for that single photon to fight its way from the center of the sun to the surface.
1 million years.
Yes. So the sunlight that is warming your face right now, that energy was generated 1 million years ago, back when Homo erectus was walking the Earth. It has been trapped inside the sun this entire time, and it just now broke free to make the final 8-minute journey to Earth.
That is just, it's humbling. But okay, let's talk about the stability. Why doesn't the star just blow itself apart? If it's a continuous nuclear bomb, why doesn't it just explode outward and disappear?
This is the beautiful, elegant concept of hydrostatic equilibrium. Hawking uses the balloon analogy here, and it works perfectly.
Well, Bean.
Think about blowing up a balloon. The air you push inside is creating pressure, pushing outward. That's the fusion. The rubber of the balloon itself is elastic, and it's trying to pull inward. That's the tension.
And the balloon stays at a certain size because those two forces are in balance.
Exactly. In a star, you have the immense force of gravity trying to crush the star inward. That's the rubber. And you have the explosive thermal and radiation pressure of nuclear fusion pushing outward. That's the air.
And they fight each other to a perfect draw.
A perfect draw. And it acts like a natural thermostat. If the star's fusion rate increases, it gets hotter and expands. But as it expands, the core gets less dense, so the fusion rate slows down. If the fusion rate drops, the star cools and gravity crushes it a bit more, which increases the core temperature and pressure, reigniting the fusion.
It self-regulates that stability.
This balance creates a stable main sequence star, like our sun, and it can remain in this state for billions of years. Hawking estimates our sun has enough hydrogen fuel in its core for about another 5 billion years.
So, to recap, we've gone from a cold, dark, incredibly thin cloud of simple hydrogen. We let gravity crush it. We spun it into a disk. We heated the core up to 10 million degrees. We ignited a quantum-assisted nuclear fire, and we achieved a perfect, self-regulating balance that lights up the solar system.
That is the recipe. That is how you bake a star from scratch.
It really changes how you look up at the sky at night.
It does. It removes the magic, perhaps, but it replaces it with a deep sense of majesty.
Which brings us to our outro. We've built the star, but what does this mean for us here on Earth?
Well, Sagan is the master of this context. He always brings it back to us. He reminds us of our scale in the cosmos. He calls us mayflies.
Mayflies.
A mayfly lives for a single day. To a mayfly, a human being is this immovable, eternal mountain that never, ever changes. We live for so long compared to them, they can't even perceive our life cycle.
And to a star.
We are the mayflies.
Yeah.
Our entire civilization, from the pyramids to the iPhone, is just a flicker of an instant in the life of a star.
But there's a connection, too, isn't there? It's not just that they are big and old and we are small and young. We are physically connected to them.
We are star stuff.
It's his most famous quote for a reason.
The hydrogen in the water in your body comes from the Big Bang. We established that. But the carbon in your cells, the oxygen in your lungs, the iron in your blood, those elements weren't made in the Big Bang.
So where do they come from?
They were cooked. They were forged in the cores of stars that lived and died long before our sun was even born. Those first generations of massive stars fused those heavier elements, then exploded in supernovae and scattered them back into the nebula, that dust we talked about earlier, so that they could be recycled into the next generation, into our solar system, into our planet, into us.
So quite literally, we are made from the nuclear waste of dead stars.
That is a very cynical way to put it. I prefer recycled stardust. But yes, without that cycle of stellar life and death, complex chemistry and therefore life would be completely impossible.
Before we wrap up, I want to leave the listener with one final thought.
Mm-hmm.
Something I found in the sources that really stuck with me.
Oh, yeah. What's that?
It's about families. We talked about the stellar nursery, the Orion Nebula. Stars aren't usually born alone, are they?
No, that's right. They're usually born in batches, in clusters, like
Yeah.
the Pleiades, the Seven Sisters. Those are a cluster of young, hot stars that are still hanging out together near where they were born.
But over time, they drift apart.
They do. The gravitational pull of the galaxy rotates them at different speeds, other stars tug on them, and eventually the family disperses across the Milky Way.
So somewhere out there.
Yes. Somewhere in the Milky Way, our sun has siblings. Dozens, maybe hundreds of other stars that were born from the exact same cloud of gas and dust at the exact same time, about 5 billion years ago. They have the same chemical composition. They are our stellar family.
But we don't know which ones they are.
We have some candidates, but it's incredibly hard to be sure. They're lost in the crowd of hundreds of billions of other stars.
So tonight, when you go outside, if it's clear, and you look up at the sky, just think about that. Any one of those points of light could be the sun's long-lost brother or sister. You might be looking at the ancient furnace that forged the very atoms in your right hand. You are looking at a history that is written in light.
And it's a history that is still being written in nebulae all across the galaxy right now as we speak.
That is all for this deep dive. Thanks for listening and keep looking up.